I want to welcome everyone to today's webinar and thank you for joining. Today's webinar topic is modeling of propellant slosh using Nastran Incompressible fluid. My name is Daniel Kaminsky. I am a business development engineer here at ATA Engineering, and I'm very happy to be joined by our own Mark Eitner for this topic. Mark is a very experienced project engineer here at ATA Engineering. Before I hand this to Mark, I just want to give a quick overview of ATA Engineering, talk a little bit about who we are and how we might be able to better support your team. So ATA is a high-value engineering services company where we help our customers tackle the toughest problems. Engineering services make up about 70% of our business, with most of that work being focused in the aerospace and defense industry. As you can see here, we do have our hands in many other industries as well. So that includes industrial and mining equipment, high-speed systems, and themed entertainment, to name a few. So who are we? Well, we are a highly skilled employee-owned company with a full-time staff of around 220 people, most of them having an advanced engineering degree, as you can see on the plot in the lower right of the slide. We have 9 national offices across the US, and as I mentioned before, we have years of experience focusing on design, analysis, and test, where we provide high-value engineering services. So this includes everything from structural design, structural dynamics, thermal, vibroacoustics, fluid dynamics, and more. Test-wise, we are the leading independent modal test group in the US, and we have a lot of experience flying our team to test article locations to conduct ground vibration testing, for example, and then using that information to help drive modal redesign. So we've talked a little bit about the engineering services side of the business. Now that leads us into the software side for ATA. So we are a Siemens VAR, or value-added reseller. So we not only sell the product, but we also provide high-class software support and training to our customers. We really focus on products and solutions that we use in-house, so primarily on our design, analysis, and test work. So for example, that includes NX for design, Femap, Simcenter 3D, and Star CCM for simulation. And for test, we are the first and now one of the only Siemens partners in the US that can provide Simcenter testing hardware and software. And one thing that really sets ATA apart is that we sell what we use. And because of that, we've seen past customers truly appreciate our expertise with all of these tools. And this has been proven over and over again through our hotline support, where you actually are speaking with a well-versed and experienced ATA engineer. In addition, we do teach a variety of classes, primarily dealing with simulation, and we actually generate all of the Siemens training material for Nastran as well. So I want to encourage everyone to visit our ATA website. You can find all kinds of information on there, including technical hotline support for our customers who have purchased software from us, as well as a bunch of free resources. So that includes past webinars, Femap APIs, white papers, and more, all of which are available to download. All right, with that being said, I'm happy to introduce today's speaker, Mark Eitner. Mark works as a project engineer focusing on loads and dynamics analysis for aerospace customers. He holds a Bachelor of Science and Master of Science in Mechanical and Aerospace Engineering, as well as a PhD in Aerospace Engineering from the University of Texas at Austin. Prior to his time at ATA, Mark performed postdoctoral research on fluid structure interaction in hypersonics. All right, take it away, Mark.
Thank you very much, Daniel. Okay, so let me just share my application window here. Yeah, thanks very much for the intro, and welcome everybody from my side as well to talk about Slosh and fluid modeling in Nastran. So let's just jump right in. I want to give a quick overview of what we're going to do today. We're going to start out with a bit of an introduction to sloshing in general, right? That term might maybe mean something to some of you, something to, or nothing to some of you as well. I then want to give a bit of a quick introduction of how you can model fluid slosh in Nastran, especially the old, let's call it almost outdated methods. And then I want to jump into that new defined fluid mass method, right, where we're using incompressible fluid to model this. We're going to go over some theory, look at some aspects of what the software and the solvers can and cannot do at the moment. And then the second part of this, I want to talk about an application example. So we built a little launch vehicle model that's loosely based on a Falcon 9, just to go through the whole process of starting with the structural FEM and then building your whole fluid finite element model, running through a solution 103 and looking and evaluating results. And in the end, there should be approximately 15-ish minutes for a questions answer session. Right. So let's jump into this. What is sloshing and why is it important? So I assume most of you, when you hear sloshing, right, maybe think of what you're seeing on the right-hand side here. This, some fluid in a container, be it a coffee mug or a tanker of some sort, right, or a launch vehicle, where the fluid has this oscillatory motion at the surface, right? So a few terms we want to talk about here. Anytime you have an interface between a liquid and a gas, right, we refer to this as the free surface of the fluid. And the disturbances, the wave-like motion at the surface, right, that's what we refer to as sloshing. And it is obviously highly important for many aspects of a finite element model to properly and accurately model both the behavior of the bulk fluid as well as the sloshing dynamics at the surface, right? Important for getting your dynamics correct and your structural loads, right? Especially in the context of launch vehicles, right? This is important where, your fluid mass can be more than 90% of your entire system mass. This is not a new problem, right? And there exist many methods to model this, but there also exist a lot of methods that are really bad. And typically fluid modeling and slosh modeling is not within the expertise of a typical structural engineer. So we want to use this quick introduction here just to give a brief overview of what this is all about. And then we can jump into the actually details of the model, the modeling aspects. So I want to give some basic slosh relations, and I want to focus on circular cylindrical tanks, mostly because they are the most common, especially when we talk about launch vehicles. And the first point I want to make here is there's a really, really great resource provided by the Southwest Research Institute. They've done decades of research on sloshing, and they've published this document called The New Dynamic Behavior of Liquids in Moving Containers. This contains a whole range of theoretical and modeling descriptions for various tank shapes. It includes information on how to model damping, on how to design slosh baffles, what the effect of slosh on guidance, navigation, and control is. So I highly recommend for anyone who hasn't read this, to use this as your primary resource for anything fluid and slosh related. Okay. If we talk about slosh, we always have to talk about gravity, right? So gravity is the restoring force on the free surface sloshing, meaning if you have a container with liquid in space where there's essentially microgravity or no acceleration at all, you're not going to have any slosh frequencies while your deformed fluid, right, has no restoring force to come back. On the other hand, if you have a rocket that's, undergoing its max acceleration, you have a very high, let's say, gravity or longitudinal acceleration technically, right? So your slosh frequencies will be relatively high. Typically, for sloshing, it's important to look at the first lateral slosh mode. So that's what is shown here in this little animation on the left, where you have this lateral left-right motion that moves a lot of the fluid around and thus produces the largest lateral loads in your system. There are equations that very accurately represent the slosh frequencies, and I'm giving here the approximation frequency for tanks that are, sufficiently high filled. There's just, you see this equation term here that has a G over R. G is your longitudinal acceleration, right? We just talked about. And then R is the tank radius. So meaning, right, if you have an enormous starship, right, you have very low slosh frequencies versus what we saw previously, right, in the coffee mug example, we have high frequencies. And when I say high, right, we're in the slosh domain. So we're talking about, between less than a hertz and maybe 3 hertz, right? So I just want to put this all into relative terms here. It's also important to know that slosh modes are really lightly damped, which is what sometimes, creates a problem for the guidance navigation team. And just also the whole reason why a lot of times in tanks you have to include additional devices such as slosh baffles to artificially increase your viscous damping. And then the last point I want to make here is that sloshing is primarily a surface effect. So I'm plotting here on the right side of this animation the pressure mode shape, essentially, associated with that slosh mode. And what you can really see is that the actual slosh dynamics primarily occur at the free surface. And as you go further and further down in the tank, there's really hardly any motion, there's pressure change occurring anymore. And you can think of this, again, going back to the coffee mug example. Imagine you put a bunch of sugar in your coffee, it all sinks to the bottom. If you're just exciting the system so that you get your first slosh mode, you're not very well distributing your sugar at the bottom, right? It's essentially motionless, right? And you only get the disturbances near the surface. So that's what you're seeing here in this pressure plot. Okay, now that we all understand what slosh is, let's look at some methods of how this could be modeled in Nastran. So it is known that there exist some simplified methods to model this, but they are not great. Let's put it this way. So the worst thing essentially you can do is you can just add non-structural mass to your tank walls, right? Assuming, okay, I have, 10 kilograms of fluid and I just smear this over the tank wall. That's pretty much a horrible way of doing this, right? It gets inertia wrong and all the interactions between fluid and structure obviously are neglected. So avoid this, obviously. The next option or method is to use a lumped mass approach. So that's essentially where you you simulate the fluid just using column 2 masses, and you connect them to the tank walls via, say, RB3 elements. And then you can also separately model just the sloshing mass itself by connecting it with a spring of the appropriate stiffness, right, to your tank walls to get the dynamics correct there. This is an appropriate method to some extent if there's not too much fluid structure interaction, meaning if your tanks are relatively stiff, that's appropriate, but we can do better. Simcenter Nastran has 2 additional methods that are meant for fluid modeling. One of them is referred to as the virtual fluid mass method, or known as mFluid. That's a boundary element method where you essentially only define the wetted surface. So that's that plot here. By the way, Daniel, can you confirm that my mouse can be seen? Just want to make sure.
Yeah, Mark. Yeah, I can see it.
Good. So the wetted surface, right, needs to be defined for the mFluid method. Typically works best on exterior fluids. So if your structure is immersed in a fluid, but you can also model internal fluids. And there's no explicit representation of slosh, okay? But it gets the bulk fluid behavior correct pretty well. The next method is the defined fluid mass method, and that's what I want to talk about. And that's where you're essentially doing an explicit representation of your fluid using a solid mesh. Okay, so this new defined fluid mass method was added in Nastran version 2306. And it is essentially builds off the acoustic fluid structure interaction capabilities within Nastran. It requires a mesh of the fluid, right? Like we just said. So you need to explicitly mesh your fluid volume, but it doesn't need to match the structure on the outside, right? It doesn't have to be exact node match between the fluid and the structure, which makes this a great method. And all of the coupling between the fluid and the structure is automatically handled within Nastran, right? So essentially, the fluid looks for the closest structural surface and couples with it. Almost always, at least in my experience, this works well without having to tell anything specifically to Nastran. If you want to make modifications, there is this AC modal card that you can include in order to maybe tell the system, okay, don't couple to this phase, or like you missed a phase, or maybe increase the search radius. So Nastran gives you the options of modifying this coupling, but usually it works extremely well. This method explicitly models the fluid sloshing if a free surface exists, right? Obviously, if you have a tank that's completely filled without any Alish gas in there, right? There's no sloshing. But if you have a free surface, this method explicitly models this. And since it came out, we've done lots of comparisons with various analytic results and other essentially DMAP-based approaches, such as our ATI hydro code, and found overall pretty decent agreement with it, as long as we use it for what it's intended. Okay, let's take a look at some theory here. So we're going to start out with the coupled structural and acoustic equations. And you're seeing here on the top, you essentially write mass times acceleration, stiffness times displacement equals your forcing vector. U represents the displacement degrees of freedom of your structure, and P is your pressure degrees of freedom. And this is straight from the essentially coupled structural acoustics equations from Nastran. The first approximation that's being made is now of fluid is incompressible, meaning essentially infinite bulk modulus. So this term here, MFF, falls away, which means that if you just look at that second line, you can express the pressure term just as a function of the structural accelerations. Okay. If you then plug this back into the first line of this equation, you end up with essentially this mass matrix times the structural elevations, or like MA plus KU equals F, right? You now have this structural mass matrix and this effective fluid mass matrix, which is a pretty dense matrix because essentially all your wetted degrees of freedom are coupled with each other. This is what Nastran then essentially solves. Typically, the regular solvers, can't handle these dense matrices well, which is why Nastran has included additional new solvers in there, which handle these better to some extent. I don't want to talk about the solver intricacies at the moment. If we have more time, we can talk about this later, but that could be a whole other talk. Sloshing is computed within Nastran by essentially creating a set of artificial grid points at the free surface. So essentially each of these nodes now gets a new degree of freedom that only has a normal degree of freedom, displacement degree of freedom. And since we already said previously, right, gravity or like acceleration is the restoring force. So the stiffness that's associated with this degree of freedom is proportional to the density of the fluid, your acceleration term, and then that area that's associated with this single node. So you can think of this as if Nastran generates this artificial grid of nodes and puts a tiny little spring on each one of these nodes. And because both the stiffness as well as the mass are proportional to the density, it means that the slosh frequencies that you compute are independent of the density of the fluid, right? So it's like a pendulum, right? Where the mass is independent, it's just a length variable. Okay, so what can the defined fluid mass method do and what can it not? So I just compiled here essentially a list, very much an incomplete list of just some issues that I'm aware of, we are aware of, that maybe some customers report. And let me just go through this list for, really quick. I want to make sure that it is clear that it could very well be that some of these issues have already been resolved, or that there are additional issues, right, that are missing from this list. So don't, take this with a grain of salt. But the fluid mass method is intended to be used for dynamic solutions 103, 111, and 112. And we can also use it to make external superelements, right? As long as your fluid and your the structure it couples with, are within that superelement. We have seen issues or problems with this method in the following aspects, right? We have you cannot run a static solution with it. Even in a stat sub case, there are issues. Pressure output for external superelements is also giving some problems. Anytime you compute pressure for the fluid nodes, it's relative to some arbitrary node that you cannot set. So just be aware of that. You cannot set the damping for the fluid at the moment, right? So the material card where you would usually define your damping, it ignores that damping value. I said the solvers that Nastran or that Siemens created are pretty decent at handling these dense matrices, but once you get to a lot of modes, right, in the 1,000 range, then it really is very, very memory hungry. So you need to do a little bit of trickery there. There's a parameter that's not supported if you want to do response dynamics or like vibrata runs. That's this ASCON. Restart currently not supported as well. And then for some of the solvers, which is this IPK and subspace folder solver, you cannot specify a frequency range. You have to specify the number of modes you want to solve for. And we're also aware of some issues with the mod ACC mode acceleration in external superelements related to this. Now, the main point I want to make here is that Siemens is very responsive to a lot of these issues. They're constantly bringing out updates, which is why we highly, highly recommend to always use the latest version of Nastran. Okay, because this is such a new method. Bugs are constantly being found, right? So we're making a constant improvement, essentially each half year. Okay, so let's jump into our launch vehicle example and kind of just walk through this whole process. Okay. So we built a model loosely based on a Falcon 9 rocket. We specifically modeled the first stage using shell elements, and modeled the upper stage and the thrust structure just using point masses with the approximate inertia, right? Connected via RBE elements. And we essentially want to model this launch vehicle at liftoff, where we're just assuming 1.4 G approximately in acceleration. Step one, we have to build the mesh, right? You can build your mesh however you want. Ideally, right, if you have an axisymmetric tank, what I typically do is, I go in the cross section, I trace the structural mesh, and then I do a 2D mesh and do a revolve operation to get a nice structured mesh from it. You can use tetrahedral mesh elements if you want to. The advantage of having a nice structured mesh is that a lot of times when you do these meshes, people ask you for various fill levels, right? Or for, I don't know, Falcon, right? Maybe you want to do, your whole CLA or other loads computations, in like 5-second increments. So you need a whole set of fill levels, and those will all be individual meshes. But by having a nice structured mesh, right, you can very easily just cut off a few elements, make a new mesh, cut off a few elements, save as a new mesh. The only thing you have to do within the mesh generation is you have to change the fluid type. I'm showing here just the Femap like GUI interface where you just go to modify, update other node type, and set this to fluid point. Okay, all this does within Nastran later. It puts the displacement coordinate system to -1, and then Nastran knows, okay, this is a fluid point. So it only has the pressure degree of freedom. Next, we want to define some properties. So we want to define a solid property, and we want to reference a fluid material with a MAT10 card. So in the MAT10 card, again, I'm showing just screenshots from the Femap user interface here. You really only need to define the density of the fluid, right? That's one of the points I said earlier. Even though MAT10 has an option to put in a damping coefficient, Nastran completely ignores this for the incompressible fluid. Okay, so what you're then in the end left with is this Nastran P solid property that has this P fluid, right? In the end. And then, like I said, all the individual grid points that refer to this mesh have the output coordinate system of -1, which tells Nastran this is a fluid point. Okay, now you want to define your free surface, right? So the free surface, right, is the interface between your liquid and your gas. So Nastran will not try to couple to structure at these faces. What you're doing is you're defining a B-surf card within Femap. Again, I'm showing the GUI here. You go to connect fluid region, and then you define the fluid as an incompressible fluid surface, and just click on all your elements that represent this surface. And make sure the surface is flat, otherwise Nastran yells at you. In these options, right, you have to tell Nastran what the gravity is, right? Because we said earlier the frequency is directly related to, right, the square root of your acceleration, right? I said previously, right, we are approximately 1.4 Gs at liftoff, right? So I'm putting 14 meters per second here, right, as the entry. And then the last important part you have to set is the component modes. So technically, right, there are hundreds of nodes on the surface, on the free surface. And if you were to just compute all the slosh modes, right, you would get one slosh mode for each one of these nodes, which is cumbersome. You definitely don't want to do this. So Nastran performs internally a component mode synthesis reduction on just the sloshing surface or slosh modes. So what you need to do is you just specify the first, n number of modes that you want to solve. And annoyingly, in the setup, the very first mode is just as an incompressibility constraint. So your first slosh mode will actually be mode number 2. So in this case, I want the first 4 slosh modes, and thus I'm putting in component modes equals 5. Okay. And then down here, right, in Nastran, you're seeing what this looks like in the actual text file. This generates this B-surf card as well as this incompressible fluid card, which tells Nastran that this is a sloshing fluid with 14 meters per second acceleration and 5 component modes. Okay, so now we can set up a solution, and in this case, we're doing a solution 1 of 3, right? So we just want to compute our modes. We need to add essentially 3 important cards that I would always suggest should be added. The first one is the fluid structure control card, and what that does, it allows you to output a separate mesh file that only shows the coupled structural and fluid phases, or elements rather, which is important purely for debugging purposes. And we will get back to what this looks like in a second on the next slide. Next, you can include the incompressible fluid options card. And that's this card down here. Here is where you define your solver that's used to solve for this dense fluid matrix. Default is this implicit Arnoldi method, IRPK. And then you can also explicitly request that the fluid mass be written to the FO6 file, which is also great for debugging. And you can also request that the free surface mesh of the fluid is also written as a separate mesh. Right? We said earlier that Nastran internally generates these grid points at the free surface and puts this spring everywhere. This yes option writes this mesh as a separate file. You can import this into your Femap, right, GUI in order to then visualize the slosh modes. Okay, some model checks that are relevant. So in the FO6 file, you will see some information about open surfaces. So towards the top, you will always see this fluid structure interface check. And essentially, Nastran is then, returning a force that's equivalent, force and moments that are equivalent to the open surfaces in your model. Meaning, ideally, you want to have your model that's perfectly coupled everywhere. That there are no gaps or holes in your structure, right? Everything is coupled properly, so that these resulting forces here, that you see, right, T1, T2, T3, they should all be relatively small. If you see some issue in here where one of them is large, right, it would indicate that in that corresponding direction, you maybe have some phase that's not coupled. Next, the FO6 file also contains the fluid mass, right? That's what we had requested previously within the incompressible fluid options card. So what that does is writes the fluid mass to the FO6. It only writes the combined mass, right? So in our Falcon 9 example, even though we have two separate fluids in here, you cannot request the mass individually, at least at the moment not. So it just gives you the combined fluid mass. But again, another sanity check. We had said previously, right? If we use this fluid structure coupling card, we can write out a mesh that shows us the coupled fluid and structural phases. It's a very useful check. I always recommend at the beginning of each solve. And what you can see here when you load this into Femap, it gives you essentially two properties, the coupled structural phases, as well as the coupled fluid phases. And you can just take a look there, spin your model and just inspect if there are any holes, or if, for example, somehow your fluid has coupled to something that it's not supposed to couple to. Comparison with analytical results, right? So again, we said previously, there exist essentially great equations that represent your slosh frequencies and for regular tank shapes. So what you can look for in the FO6 file is the solution of the sloshing frequencies by themselves, right? So that's what this component mode synthesis reduction does. Essentially, at the beginning, it computes just the slosh frequencies without any fluid structure interaction. So imagine as if you had a perfectly rigid tank. It computes just the slosh frequencies. Again, right, we had previously requested 5 component modes. Let me just go back here real quick where we did this here, right? So when we defined the free surface, we had requested 5 component modes. So later on in your FO6 file, you're going to see these eigenvalues, and you see 5 of them. And again, the first one you neglect. The second one is your actual first sloshing mode, and we are at 0.6 Hertz, which matches, just a simplified equation here. So again, another sanity check, just to make sure, right, all your results make sense. Okay, and then in the end, when you have your solution, you can visualize the results. And right, we said before that Nastran internally generates essentially a new mesh on the free surface with fluid degrees of freedom that have, just a normal displacement degrees of freedom. In the FO6 file, Nastran tells you how many grids it internally generated, how many elements it generated, and what the numeric ranges are for those. Just be aware that, if you're, it could be that these numbers are, higher than 99 million. And since Nastran writes this file as in short field format, right, you run into issues there. So just a little caveat that, I've personally had to deal with several times. Let me quickly go into into Femap just to kind of take a look at what the solution looks like. Okay, so all I did here is I took our model and I loaded the structure, I loaded the fluid, right, separate like include files, and then I also imported the internally generated mesh, right? So that's this essentially solution underscore plot L dot dat file. So what just to highlight this, right? This just represents the nodes and then the plot elements that represent the sloshing surface. So I loaded the solution 103 results in here. If I click on, animate mode shape for the first mode, what you're going to see is that the fluid, the solid fluid mesh, does not move, right? Why is that? Well, as we said before, the fluid degrees for the fluid only has pressure degrees of freedom, right? It doesn't have any displacement degrees of freedom. So you won't see any mode shape result associated with that. But that's exactly what this underscore plot L dot dat mesh is for, right? So if we're hiding now the fluid elements, now you can see the slosh motion on these plot L files, right? So we can see here now let me just maybe highlight do contour and just show the plot Ls. Yeah, right? So this is showing now the first bending modus and the sloshing because they have similar frequencies for this model, right? They implicitly they couple. And you're gonna have, if we move through here, right, you're gonna have the slosh modes that always appear in pairs, right, in both lateral directions. What's this? Okay, because we don't have any tank pressure in here, right? You get these shell modes of the structure. At some point, then we get more slosh modes. Yeah. So depending on what your structure is like, right, either you have all the slosh modes bundled up, below the 1 Hertz range, and then sometime later you get to your actual structural modes, but for large enough launch vehicles they are somewhat in the similar range, which is why slosh modeling obviously is important. Okay, let me just go back to my presentation here, but that is the main thing of what I had prepared. So yeah, I'm essentially good on time, pretty much. Ready to open this up for any questions you may have.
Yeah, like I said, a good amount of questions have come in. I'll probably just go in order here of when they were typed. If you do have additional questions, anyone, please go ahead and add them to the chat. I know I saw Ryan Denton, you raised your hand at some point. If you do have a question, please go ahead and type that in. Okay, so starting, looks like Eric Rollo was the first person. Eric had posted a handful of questions. In the interest of getting to everyone's, we'll maybe just focus on one or two of them. So first question was, how do I get pressure profiles out of the analysis? I can't seem to be able to do it for sine vibe and random vibration runs.
So we have run into pressure issues only when we try to use this with external super elements. I have personally not encountered issues with pressure in any other case. And I'm gonna let sorry, were you gonna say something, Daniel?
Oh, I was going to say, yeah, maybe Eric, if that is still an issue you're seeing, maybe you can just give us more details over that, like I said, email after the webinar, and we can try and get sorted what's going on with your solve. Does that sound good, Mark?
Yeah, definitely. And I want to give our other slosh expert here, Ken Ferguson, is on the call as well. Ken, if you are able to answer any of these that where I'm just blanking on, or like you have some experience, feel free to chime in here as well.
All right. Yep, sounds great. Yeah, let's do one more of Eric's questions. Let's see. He has models that are taking 11 hours to solve, and they'll only get up to 65 modes. And this is with 192 gigabytes of RAM and 48 cores. Are there some correct solver parameters or optimization things you can do to deal with those solve times?
We have so I mean the one comment on solvers, I guess that's a slide we didn't go through here. Maybe just for everybody else's benefit. Right, I said before that typically, right, you would do your eigen solutions using the trusty length source method, which deals well with sparse solutions. But because we have such dense matrices now, right, with all these coupled wetted faces, Siemens has included these three additional methods here, right? The subspace, result annulity, and the dry modes method. All of them maybe have different advantages, disadvantages, and yes, can be memory hungry depending on obviously how dense the matrix is and how many modes you're solving for. We've seen a lot of customer inquiries asking about these. There's no clear solution, that like once over, always the best results, always the fastest. A lot of times we try to give customers the suggestion to try and put their fluid tank models within a super element, external super element, right? Then you can use one of those three solvers to just solve the tank itself, right? And then you can use the regular length source method later on for your whole system fam. Sometimes it works, sometimes it doesn't, right? Depending on how much connection there is, or how finely integrated, right, your tanks are in your structure. But there's for sure no like very clear answer. We know that Siemens is working on it. That's essentially all we know, or all we can clearly say.
All right, thanks, Mark. Let's see. Christian, and sorry if my apologies if I pronounce anyone's name incorrectly. Christian Bemrand, on slide 4, he asked, is it true that the first natural frequency calculation would only be true for tanks oriented in the upright position? If so, is there another easy first mode calc for tanks on their side?
So yes, it is true. This is the equation for axisymmetric tanks in this orientation. So I'm not aware of tank on its side slosh solutions, mostly because I don't typically encounter this. You have to be careful at some point, right? If you're taking this tank, for example, let's say, right, if you have your tank, if you put it on its side, you have this huge surface, that free surface where you essentially can have sloshing, right? at some point you no longer have a regular, slosh mode, but rather you have these traveling waves. Right? Think of it like a swimming pool, right? Waves in a swimming pool, they don't just behave like slosh waves. We have these traveling waves, which is completely different. Yeah, I guess methodology, math behind it, right? So this no longer applies. I don't know off the top of my head if the Southwest Research Institute has an equation for that. But if it exists, it would be in this document.
All right. Christian did have another question. Let me go ahead and maybe ask one of those then as well. Can you elaborate on the lack of fluid damping? Is there some inherent damping associated with slosh modes? Um, when it has that lack
So,
of damping term, has that caused difficulties in modal accuracy?
so in yes, so we know that slosh modes are very lightly damped. You can find equations for damping approximations of I think only the first lateral slosh mode that are essentially based on experimental correlations that work pretty well. Uh, if you are lucky enough that your slosh modes are all well separated from your structural modes, then you could just essentially set a damping schedule. I guess I don't know if you're solving this with vibrata, right? You just say, okay, modes between 0 and 2 hertz have 0.1% damping or whatever you calculate for this equation, right? And then anything else, it's your structure. You can define your regular structural damping however you want to. But there's no material property that you can define that would automatically then give you these damping results. I know some people have written their own DMAP to get around that, but there's no inherent Nastran way of dealing with this.
All right, thanks, Mark. Steve Johnston had asked, is this leveraging ACTRAN solvers for the fluid structure interaction?
I am actually not aware of or familiar with AppTran solvers. Ken, do you have any insight into that?
No, I'm not familiar with it either.
Yeah, so these are the
Okay.
three solvers that are officially used. That is what I'm aware of.
All right. Let's see. Uh, yeah, Semel, again, apologies for any uh, incorrect pronunciations of names here. Semel had asked, when creating a reduced fuel tank model in SimCenter Nastran, for example, MAD-OP4 super element, what is the recommended workflow to ensure that both the structural dynamics and the fluid slosh modes are retained in the reduced model? Any particular considerations or limitations?
Ken, do you want to jump in on that? From a setup point, I just know that you have to include all your coupled structural and fluid elements in there, otherwise it won't work. But from a suggested approach for proper modeling, yeah, Ken, I'll let you jump in there.
Right. Like you said, you can't create a super element of just the fluid, so you would be including your structural model of the tanks as well as the fluid. Um, and when you're reducing your super element, you would be using these incompressible fluid options shown here and the solvers there. But other than that, uh, not using any specific special considerations to create the super element other than what you'd normally do.
Thanks, Ken.
All right. Thank you. Eric Stewart asked, and I think I've seen at least two of this type of question. Is there a rule of thumb for how dense the fluid density, mesh density should be? A dense fluid mesh will greatly increase computational cost of the analysis.
Yes, I agree. We have not come up with a rule of thumb yet. I think that's very much customer dependent on how large your system is. And we have not encountered, I guess, a wide variety enough to make this assumption, but create a rule of thumb. But I fully agree. You're very much right that this will drastically increase your solve times and memory. Sorry.
All right. Thanks, Mark. Brandon had asked to go back for a screenshot. Just so everyone's aware, this presentation will be posted on our website, and an email will go out to all of the attendees once this webinar is done. So if you need to get any screenshots or review the material, watch the webinar again, you'll be able to do that. Again, an email will go out. I'm also posting the link right now to where the webinar will be posted on our website, so you'll be able to find it there. Okay, continuing here, we have a question from Nino. Handful of questions here. Let's see. First question is, how many elements should the fluid be modeled with in the radial direction? So I guess another kind of meshing related question.
Yeah, true. I think I would suggest 5 at least. And at least that's what I've always had decent results with. Let's see, where's my mesh? Here. So the easiest, I guess, convergence study you could do is you can make that, if you look at your results, right, of your slosh modes, right, these should mostly match your theoretical equation. Right, so these are the slosh modes of that in that component mode, since this reduction, which don't have any fluid structure interaction, it's just slosh itself. So these should match well with your theoretical equations for your specific tank geometry. Yes, here we're seeing, right, 0.6 and versus 0.608. If that's insufficient for you, then yes, maybe you might have to include an additional element. But 5-ish, right, is like the rule of thumb I've always used.
All right. One additional question from Nino. I noted that the fluid eigenvalues often come in pairs. Mode 2 and 3 are the same, and then mode 4 and 5. Is this a coincidence, or what particular details are going on there?
No, that's exactly it. It's the same idea as with a kind of axisymmetric model, beam bending, right? You always have your bending modes that come in pairs. So that's as it should be, right? Especially in the fluid-only modes, the slosh modes that you see in the beginning, right? Those should for sure come in pairs. Later on in your full eigen value analysis, where it couples those with the actual structure, yes, then you might see maybe a little bit of a shift, which comes from structural modes not being, perfectly in pairs.
All right. Great. Thanks, Mark. Let's see, question from Peter Grimer. Would you typically run the Sol 103 with the gravity set to various levels to span the full launch environment?
Yes, so what I typically do is when I receive the structural mesh from a customer or internally, right? I make my set of meshes usually in about 5% increments, right? So I'm creating essentially 20 or 21 different fluid meshes for each of the tanks. And then within each of these individual fluid meshes, I modify the gravity card, right? So let's see here. Well, right? So in the end, I have a whole folder of these include files. Each of them represents one of these tank fill levels. Each of the tank fill or tank levels has an associated free surface, and that free surface, right, has an associated acceleration value, and that's usually right provided from some trajectory file, right? That's my workflow. Of course, it depends on right where you're getting the trajectory file from, or yeah, I guess how tightly your interaction is with the person who does that computation. Just make sure whenever you provide a fluid model, you tell the person that this is only valid for a specific acceleration value. And if they want to change that, right, then they just only have to go into the incompressible fluid card and modify this value here.
All right, great. There was a question about providing DAT files. I think there'd be no problem with providing these DAT files, right, Mark? Okay.
Right.
Yeah, so if anyone's interested in it, again, you can just email me directly after the webinar, and we can make sure can send those files your way. Next question, Ramsey Eunice asked, when using defined fluid mass, I found that the recovery data blocks are big as they're supposed to be. For example, if I request 20 modes, I'll get 40 modes of OUG, where the second half are all zeros. Is that expected?
Oh, I've run into this as well. I don't have a solution for this, but I've noticed this as well. I don't know what the issue is with this, or whether or not Siemens is dealing with this. Yeah, so I'm aware of it. Don't have a solution for it. Don't even know if it's a bug or it's intended.
All right. Let's see. Next question from Brent. The gravity entry on the fluid card. How does this relate to a body load applied to the overall model, and how is the direction of the gravity entry defined?
So the direction of the gravity entry is always normal to the free surface. So your free surface has to be flat, right? So there cannot be any ambiguity. I think there's an internal tolerance level of 1 degree. And once you go above that, Nastran yelled you. The acceleration vector is then applied normal to this free surface. And that's completely independent of anything outside if you apply a graph load or something. So your slosh frequencies will only be computed based on what is in the incompressible fluid card.
All right, thanks, Mark. Let's see. Seymour had a follow-up from his question. He, just wanted to reiterate his priority really is that the MAT OP4 card for the reduced fuel tank workflow. Yeah, let me see if I could go back and look at his first question here. Yeah, so when using the MAT OP4 super element, recommend flow. Again, maybe that's just something that we could provide additional details after the webinar. What are your thoughts there, Mark?
We're happy to answer emails, right, about some of these specific aspects, because obviously, right, we can get very well into the weeds.
Yeah. Okay. Yeah. So I think on that one, feel free to just go ahead and, like I said, reach out to me directly. I had just posted my email again, as well as another email, but you can just free to send it to the Daniel Kaminsky one, and I'll make sure Mark gets those questions. Okay, moving forward here. Yeah, tons of great questions. Again, I know we're at time here, so or the original allotted time, Mark and I talked about this before. We're okay with keeping going and answering questions, but again, if anyone has to jump off, please just feel free to send questions to me. that you want answered, or like we said, if you wanted that model file, just email me and we'll be able to provide that. Okay, next question was from Felipe. He said, Mark, you said that you need to include both the structure and the fluid model in order to create a super element for use in dynamic analysis. Have you explored trying to rig up a way to just super element the fluid model? This would be a similar paradigm to what I've used with the ATA Hydro.
So yes, we have, I think, started to think about this, or rather, one of our, Paul Bladlock here at ATA had played with the idea. We have not explored this further. That's the state of our advancement on that. We've had this discussion on if there's a way to kind of cheat your way around it to get more Hydra-like. Ken, yeah, feel free to jump in there if you've done anything separately.
Yeah, no, currently you can't have the fluid nodes in the B set of a super element. That's not allowed. So you can't just you can't just try to make a super element of the fluid directly. Yeah, like Mark said, like we've discussed some tricks to try to get around this, but we haven't really made any progress, and certainly nothing that we can competently say that will work. Yeah.
All right. Great. Thank you, Ken and Mark. Sorry, before getting back to questions, I saw that Christian just said he's not seen any posts of emails or anything by the hosts. I guess Ken or Mark, have you been able to see my email postings in the chat?
I see you posted a link at 10:53.
Yeah, there should have been another one at 11.
At 11,
that is
no,
odd.
Oh, yeah, no. I'm seeing this. No, confirm. At 11, I'm seeing.
Okay. Okay, sounds good. Christian, if you aren't able to see it, yeah, like I said, there should be going an email after this webinar that you should be able to see it. Or I guess a few people say they can't. That is odd. Oh, it might be my filter, my chat filter. I think that is the problem. There we go. Sorry about that. It defaulted to a filter of who can see it. Sorry about that. Thanks everyone for letting me know. Okay, so sorry, jumping back into questions here. We have a question from John Shoemaker. Are there any modifications to this method for approximating diaphragms constraining the fluid-free surface?
Yeah, so diaphragm just means that essentially you no longer have a free surface, right? Because there's no longer, you now have an actual structure that couples with your fluid, right? So in theory, you can just run your entire solution as an enclosed fluid, right? So in your which slide was this? Here, right? So when you set up your fluid, you no longer have this free surface allow sloshing option, but rather it will be in enclosed fluid. So it's assuming either the tank is fully filled, which is kind of what a diaphragm is, right? It's a very compliant element on the top. If you want to, so it's not going to compute separately slosh modes, but it's just going to compute the fluid structure coupled modes. If you want to still call that sloshing, I mean, I guess that's technically not really correct. Though I think I've only tried it once, and we ended up running this as a free surface anyway, because we had so little information about the membrane. So this was a particular issue there. I suppose if you have enough information about the stiffness of your membrane, yes, then you would just change this free surface to enclosed. This will just in here in the incompressible fluid card. I think it'll put ENCL or something instead of the slosh. You don't have to include, any gravity or any component modes in here. I suppose at some point, right, in the, limit as your diaphragm becomes infinitely compliant, right, then you're back to an actual slosh solution. So you might have to evaluate, how close to that limit you are. That's what I can say about that.
All right, thanks, Mark. Next question. I think we kind of touched on this, but maybe you can reiterate again. How would you consider slosh if your orientation of gravity vector were changing?
So I guess that depends on how much your gravity vector changes, right? So typically on a launch vehicle, right, you never perfectly, your acceleration is never perfectly along the longitudinal axis, right? You might fly at some small angle of attack, maybe 4-ish degrees. Typically that's totally appropriate. Once you get to some, larger angle than that, yeah, you might have to remesh your fluid mesh to account for, that actual shift. And let's say if this tank were flying at 30° something, right? Then yes, your free surface would no longer be oriented like this, but would rather be, angled. And then you can ideally just rerun your solution like this. You won't have any, analytical results to compare to. But we have not tested this at any, if the method, complains at any large angles. It shouldn't, but we haven't tested this.
All right. Next question comes from Neil Gordon. Would this method work for baffle evaluation? It doesn't seem like it, but he was curious.
Yeah, I thought about this as well. In principle, if you have a super fine fluid mesh and are able to properly resolve your, I guess, the small geometry, depending on right how large your baffle is, right? If you just have radial baffles that are a few percent of the diameter, yeah, you would just need a much smaller fluid mesh, and then you can evaluate whether or not your elements are properly coupling. You might have to, yeah, I guess in your fluid mesh, you might have to explicitly cut out the baffle to make sure it's properly coupling. And then I don't know if the fluid can couple to, if you only have a single layer of elements that represent your baffle, I'm not sure if the fluid can couple both on the top and on the bottom. So maybe you would have to do like 2 plate elements, stacked. All I can say is I have not tried it. For sure, you will not get damping out of this, right? You might be able to get your, I guess, dynamics out of there if you're interested in doing loads or stress analysis of your baffles by themselves, right?
Okay, thanks, Mark. Neil had also asked, so Sol 111 and 112 supported.
They are supported. I have run, I think I've run Sol 112 for sure, model transient. I haven't done a 111, so I don't have more insight into that. But supposedly, and if you look on the Nastran website, they give some example problems as well for running each of these. I just can't speak to any issues related to that we've experienced.
Okay, and then looks like there was one more from Neil. He said, most CFD engineers would probably scoff at this method and could be a tough sell for those unfamiliar with it. Do we have any success stories of using the method for slosh dynamics? It seems like a great tool with a couple external to couple with external modal tools such as Z-Arrow. to better capture structural modes with fluid dynamics.
Yeah, absolutely right. A CFD slosh analysis is obviously extremely expensive, and you can have multiple aspects of sloshing that cannot be computed with this, right? If you're a satellite in space at microgravity, and then you're starting your engines, right? And you want to see what your fluid does, right? Obviously, those type of simulations are completely out of the realm of anything that this method is able to do. But it covers a wide range of problems associated with them, with what most dynamics engineers want to know, right? Like, what are my modes of the system? What are my equivalent tank or my tank loads from there? But yes, it is not CFD, right? Which is both a disadvantage or an advantage to many.
All right. We had another question from Aditya. Let's see. I have this method of slosh modeling in my tank, and have made an external super element out of the tank. The modal effective mass looks realistic for the tanks in the individual model as well as the global Sol 103 model. But is there any way to confirm the slosh modes are behaving properly besides looking at the SPC force PSD?
I suppose when you do your original super element reduction, right, it should show you in the FO6 file whether or not you're getting, I guess you can do all your regular checks on before while you do the reduction, right? I don't know if there's additional checks that you could perform on the full system modes run once you have the reduction in there. Yeah, I can't think of any at the moment. Ken, do you have any idea?
So I've been using Param, SE, Comb, yes, so I can well, in addition to requesting all displacements on tank nodes. So then you can visualize the modes and in your residual run. And I've been also using this method to do subsequent acoustic analysis. So that's one workaround. So you would be able to see the mode shapes of the tanks in that situation, as well as you could import that free surface
Plot L
yes,
file.
the plot element, and so you could visualize the slosh modes there. So you could run it both ways, and then additionally you could run it both ways, with the super element, without the super element, and compare modes on a smaller subset of modes.
True. Thanks, Ken.
All right. Thank you both. All right. I think we're almost there. And again, any remaining questions, please feel free to email. And there will also be that, like I mentioned before, that follow-up email going out with links to the webinar. Okay. Any insight on when the slosh modeling is worth doing, potentially related to radius of the tank and or pressure in the vessel?
Related to radius in the tank, I guess it's mostly an issue so sometimes your GNC team, right, will just require it, right? They want to know about slosh, right, because it's relevant for their algorithms. From a loads perspective, right, I guess if you have a super stiff tank, right, several inches of steel, right, in a small diameter, then yes, maybe it's not that relevant to look at, slosh dynamics in there. For launch vehicles, I mean, rockets, up to small missiles, well, I guess that gets into the realm of what you're interested in, right? So it kind of depends. If you're looking for a rule of thumb, I don't have one for that. But supposedly, right, you can look at your mole effective mass of how much fluid will actually be moving around, and then you make a decision on whether or not that's relevant. From a tank pressure perspective, well, that gets into a whole other topic there. Then you, of course, right, tank pressure increases your shell frequencies in a tank, so they move further away from the slosh frequencies. So they don't really have any effect on, the slosh mass or slosh frequencies, right? Like that's completely separate. That's my, thought on that.
All right, thanks, Mark. All right, I think final question here. Another one related to meshing. So in regards to the fluid mesh, should the mesh be at least be uniform in the baffle, kind of going back to the baffle discussion? Can you vary mesh density near finer features, or is that unwise / not recommended?
I don't have a recommendation because I have not tried it yet. I've played with the idea, and I would for sure encourage not, if I were to do it, I would not have a super fine mesh for the entire tank. That would just blow up your solvers. I don't know how problematic it is for Nastran to handle various different element sizes within your fluid mesh. But yes, I would very much avoid having an extremely fine mesh throughout the entire fluid volume. But yeah, recommendation, but not based on, me having any actual results there.
All right. So with that, we are 20 minutes after the hour here. So yeah, I think that's a good place to stop. Tons of great questions. So yeah, I just want to thank everyone again for joining. I want to thank our presenter, Mark, for his time. Also, Ken, thank you for answering some questions as well. Again, there will be a follow-up email coming out where to find a recording of the presentation. Once again, feel free to directly email me with additional questions or requests regarding this webinar, and I'll be sure to send those Mark's way. And yeah, that is it. Thank you, everyone, again.